Okay, guys, let's start. I presume that you watched on video the chapter on recurrent networks, right? And this is something that you are going to see also in the tutorial. And I would like to show you one, I think, important issue or important topic that is related to word models or to sequence models that is probably the hallmark for RNNs in general. So I would like to show you what is typically known in the literature as word embeddings. And let me present it in a very different way from what it is typically presented in the literature, because in the literature it always appears from the perspective of NLP, natural language processing. I would like to show it through a very different application. Okay. And again, I'm not showing all the details and tricks of word embeddings, because usually you can just call a few functions that will do the job, but just to understand the learning problem that lies behind. And this will be a segue to the topic of basically how to learn without labels, how to do unsupervised learning. Okay, so let's start with some text application. Suppose we have a sentence. Let's say we have a sentence. Okay, something like this. I think we are missing. Let's make it an A. Okay, by the way, this particular sentence is funny because it involves all the letters of the Latin alphabet. So pay attention that you have Z, you have Y, you have W, and so on. But anyway, it's just a sentence. Now let's think how we work with it. For example, if we want to do a sequence modeling, in the video lecture, I think I mentioned a few examples of automatic machine translation, things like that. One of the important issues that we immediately face when we take this as the input is how to represent our data. Okay, so the representation is quite crucial in language processing. One of the ways, I think I showed you examples in the lecture, is just to think of this sentence character by character. So I'm generating my input character by character. This is a very naive approach, of course. Still, it does some work. But again, this is not how typically we treat language. The way we typically treat language is we create a vocabulary. So let's say we have a vocabulary. Let's call it V. I have a vocabulary. It's just a set, a discrete, a finite set of words. Let's call them 1 to n. So I'm going to give each word a discrete label. Okay, and then let's say I will call this word W1, and this W2, and this W3, W4, W5, W6, W7, W8, and W9. Let's say W1 will be 514. I'm just inventing a number. Okay, so let's say the word the corresponds to index 514 in my vocabulary. And let's say quick, the word quick, W2, let's say 3,527. I'm just making up a number. So it doesn't matter in which order it should somehow matter in which order you organize your vocabulary, but let's say we just take a big corpus of English text. Let's say we Google for it, or we take, I don't know, Shakespeare's works. We just do a histogram of all the words. Of course, we need to tokenize the phrases. We need to remove the white spaces to understand where the word starts and where the word ends. You don't need learning for that. This is pretty standard text processing. You do it with standard tools, regular expressions and stuff like that. So suppose you now have tokenized words. You can create a histogram of all the words that you have in the corpus. Let's say you order your vocabulary from the most common words to the rarest words, like, I don't know, the word CGD, for example. something like that. Those are some weird words that you never encounter in anything common. Of course, the articles, prepositions will be the most frequent words that you find in your vocabulary. But the problem is, when you look at your text from this perspective, you don't have any semantic meaning. You don't have any connection between the semantic similarity of words and the similarity of these indices. For example, if you take wi minus wj, let's say you take the Euclidean distance, right, between the two indices, this is not related in any sense to the similarity, to the semantic similarity of the words. Okay? And actually, if you are working in, essentially, the words are represented as numbers in R1, right, on the real line, or even it's a subset of the real line. These are just natural numbers. It's very difficult to establish any useful metric on the real line that will somehow encode the semantic similarity. This space is too restricted for such a task. So basically what I'm interested in, I would like to construct, first of all, a metric structure. I would like to construct a metric, a distance function, that somehow will correlate to the semantic similarity of the words. So for example, I would like somehow the distance between words like, for example, war and conflict, and say strive, or strife, let's say these are nouns, I would like these words somehow to be close in the sense of this metric that I would like to create. Okay? For example, and the word peace, for example, should be distant because it's opposite. So this is the metric structure. I would probably also like some sort of a vector structure. Basically, I would like to be able to operate with vectors. And in vectors, I can do simple calculus of words. For example, what happens if I add two words, or if I compute a difference between two words and then add this difference to some other word? So can it give me something useful? Okay. So this is something that I would like to do, and the way to do it is what is called word embedding. So essentially, a word embedding will be a map. Let's call it, let me call it theta. I will call it theta just because this is the way we represent our parameters. It will be a map from V to some high dimensional space. Let's say N will be typically, again, this is not something that you select based on some mathematical reasoning, it's just trial and error, but typically it will be in the range of, let's say, a few hundreds, maybe up to 1,000. Okay? But you definitely want this to be a high-dimensional space because you want complicated relations to be encoded in the metric structure. So this thing comes with a natural metric, right? It comes with a Euclidean metric. You can use some other metric. But essentially now, instead of having a word W, you have a word that I will call, I will denote by theta W. So it's the map, it's the image of this embedding of the word W. So each word, let's say the word fox, in our previous sentence, will be embedded in some, let's say, 100-dimensional vector. Okay? It will be represented in this vector space. Okay? Now, of course, we need also to construct a metric. There is the natural candidate for the Euclidean metric. Typically, people doing language and text analysis prefer a different type of similarity. Instead of talking, a metric is a dissimilarity function. The bigger is the number, the less similar, the bigger is the distance, the less similar the two words are. Typically, in the language processing community, you will find definitions of similarity rather than dissimilarity. So let's call this S. S between the similarity between theta and theta prime, two word embeddings, is very often defined as what is called a cosine similarity. So cosine similarity, we take a vector theta, we normalize it by its Euclidean length, and we do the dot product with the other normalized vector. Okay, and you can think of it as first projecting your vector onto the n-1 dimensional sphere. This is S n-1, capital n-1, and then measuring the cosine of the angle. So the dot product measures the cosine of the angle between the two vectors. So this is the normalized theta, this is the normalized theta prime. Okay? So when two words are similar, you are expecting S to be approximately 1, right? So this is similar. If the words are dissimilar, what is the lowest value? It's -1, right? Two opposite directions. Basically, it's collinear vectors, but opposing directions. And you can, of course, relate this notion of similarity to the standard geodesic distance on the sphere, the standard way you define metrics on the sphere. But when I'm a little bit cheating because it is not a metric on Rn. You might have multiple vectors that point in the same direction and have different length that will be mapped into the same point. So it's not exactly a metric, it's what is called pseudometric mathematically, because if you have metric equals 0, it doesn't mean that this is the same point. Okay, but it will be sufficient for our purpose. So the way we are going to establish this word embedding, of course, you can just put it by hand, some way manually constructing this semantic structure, basically encoded in this metric. But this is a Sisyphean task. It's very difficult to do it manually. We are going to learn this embedding. Okay. So that's why I denoted the embedding coordinates by theta. These are our learning parameters. Okay. So essentially what we are doing, we are interested in, this is the object that we are interested in, right? So let me define as, I'm abusing the notation here. I am interested in measuring the similarity between two words. Instead, I'm going to measure some standard metric, let's call it the cosine distance, between two word embeddings. Let me write it directly, not as a cosine, but as the dot product of two word embeddings. Okay? So I'm interested in this object, and the way I'm realizing it through first embedding my words into a standard metric space, and then applying some standard metric. So essentially, I'm taking my domain of words, and I'm mapping it to the sphere. I'm thinking of my space as of a sphere. And this embedding can be very crazy. Let me draw something crazy. Okay? But now here I'm using standard distance on the sphere. Okay? So basically all the complexity goes inside this embedding. This is my theta. This is where I can encode all the intricate structure that I have in the data, all the intricate semantic relations between the words. Okay? Now this problem is not specific to language processing. This is called metric learning. I would like to learn a distance function. So I would like to view this word embedding problem as an instance, as a particular case of metric learning. And again, the way typically metric learning is performed, I allow all my degrees of freedom in the embedding, and then I use some standard metric, typically the Euclidean metric or this cosine distance on the sphere. So all the complexity goes into the embedding. Now let's ask ourselves, how do we perform this metric learning? How do we basically, what is the learning task? So we know what are our learning variables. What is the learning task? So let's see how we would typically like to proceed. So suppose I have some word. This is my domain of words. Okay. It doesn't matter that all my words lie on the real axis or in the set of indices. Okay, let me draw it as some abstract space. I would like to embed my words into Rn or into the sphere, doesn't matter. Okay. Now suppose I have a word W. And suppose I have a word that is semantically similar to this W. Let me write it here. Okay. So let's say W is embedded into this point theta W. And let's call this word, I will call it W plus. So I'm calling it W plus because it is, together with W, they form a pair that I can call a positive pair. They are similar. I know that they are similar. For example, these words are, for example, war and conflict. Okay. Sorry for the militant associations. And I'm going to embed, so now you tell me where I'm going to embed this word. I would like to embed it ideally to the same point, but essentially I would like it to be close to the theta W in the sense of this standard metric that I'm using here, in, let's say, in the sense of the cosine similarity. Okay? So the distance here should be small. I would like to minimize this distance, right? So this already tells us how our learning objective should look like. And suppose I have another word. I will denote it by W minus. Let's say this word is peace, which arguably is different from war, right? So it should be embedded distant from theta W, right? So this is theta W minus. Okay? And again, I would like to work on this map. Okay? So essentially, I translated my problem into the problem of binary classification on pairs, or if you will, on triplets. So I have data of this form, W, W plus, and W minus, right? And I know the relation between them. These are similar. Think of them as a positive class. And these are dissimilar. Think of them as the negative class. Okay? So the way typically the way we typically structure our metric learning, suppose we have this very complicated embedding. In comes the word, out comes the embedding. Okay? I'm going to take this triplet. So this is W, this is W plus, this is W minus. Okay? And I'm going to compute a loss function here. Let me define it in a second. There will be some loss function here. Okay? Essentially, the loss function would request these two to be close and these two to be distant. Right? And these two to be distant. Right? But what is important is that these parameters are shared. It's the same parameter. I'm doing the same embedding for all the words, right? So essentially, it's just an instance of this map replicated 3 times, instantiated 3 times, okay? And for this reason, this is called a Siamese architecture, like Siamese twins, okay? Now, this is how you would typically proceed in the general metric learning problem. You typically have some continuous space here. It's a vector space, some vector representation of your input objects, and you would like to do some very intricate map of these vector valued objects into some other vector space in such a way that this loss is minimized with respect to some standard metric that you apply on the target space. Our case is slightly different. So typically you will do essentially a regression network here. It will be some neural network that is parameterized by some set of parameters. In our case, we are a little bit different. We are embedding a finite discrete set of words. And it is usually not a good idea to think of some kind of interpolation problem between these words because there is nothing between these indices. If we have a word corresponding to index 5 and a word corresponding to index 6, there is no meaning to giving a value to the point 5.2. No meaning. There is no word there. So what we are going to do, we are simply going to keep the embedding coordinates for every single word in our vocabulary. I'm going to think of my embedding as a big matrix. It's an, how did we denote the coordinates? It's an n by, sorry, it's an n by n matrix. N is the number of embedding dimensions. And this is the vocabulary size. Okay? So this is the embedding of the first word, and this is the embedding of the last word. Okay, this is my matrix. These are column vectors. Okay. So these are going to be my embedding coordinates. Essentially, I'm specifying the embeddings of all the words that I have in the vocabulary, and I'm assuming that there are no other words except those that I put in my vocabulary. Okay. Now we can define, obviously, it's a binary classification problem. Now we have a straightforward parameterization of our problem. Basically, all our degrees of freedom are explicitly written here. These are optimization variables. So again, we would like W and W plus to be assigned the label 1, and we want W and W minus to be assigned the label -1, right? So let's think of this as a binary classification problem. Define a probability function parameterized by our optimization variable theta. Let's call it p hat, as we denoted in the lecture. So the probability of two words, W and W prime, receiving the label 1 will be, let me write it for now without the normalization. Let's put the normalization afterwards. I'm just using a softmax or a logistic regression function. It's the obvious choice in this case. There will be some temperature constant here, right? Something that it's a meta parameter that we tune. And here the score between the two embeddings, theta W prime. So if W and W prime are close to each other, I would like this score to be close to 1, and this exponential will be big. Essentially, I'm giving high probability to this pair being labeled as 1, as a positive pair, which is exactly what I need, right? And then, of course, the complementary probability will be just 1 minus this thing, right? And I'm not writing what is in the denominator here. You just sum these two quantities up, and basically, and you normalize, right? So we just get the correct probability. So what we typically formulate for this metric learning problem is the triplet loss. The triplet loss, again, it will be an expectation of. Typically, we'll take the log of these probabilities as we do in binary classification. Expectation is taken over all the triplets. Log p theta 1 of W and W prime. Right? Should be the other way around. So you tell me, you would like to minimize this probability, right? You'd like to minimize this probability, so you want to put 1 or 0, you tell me? Let me write the two terms. I need a minus sign here. So I would like to maximize the probability of W and W plus being classified as 1. So I would like to minimize this over theta, right? So I would like to minimize the negative log of this probability, right? And the same for the negative pair for W and W minus. But now the label 0 or -1 goes here. I think I denoted it by -1. Let's write -1 here. Okay. So this is the typical metric learning setting. It is called the triplet loss. Essentially, we construct this Siamese architecture, and we train it with this triplet loss. Okay, this is how we learn distance functions. Now, the problem in the case of word embeddings is, where do you take the labels from? Of course, you see, you need these triplets. You need these triplets. It means that for every word W that you take, somebody needs to tell you what are the positive words and what are the negative words, right? You need to form these triplets to do the learning. Okay? So if I just take a corpus of text, of course I have many, many words in sentences, but there is no labeling of positive and negative pairs. You could do it by hand. It would be a really monumental work to do these type of annotations. Okay, so essentially we have a learning scheme how to translate these labels into a metric structure, but the problem is where do the labels come from in the first place. Okay, so the trick that is done in the NLP community, you take the text, you take for example the sentence, what was the sentence there, the quick brown fox jumps and so on, right? So we are not going to group words by similarity. That would be quite complicated, and sometimes it is even impossible. For example, the word go in English means the verb to go, right? Means motion, but it's also the game, the go game, right? That you play on a chessboard. So in different contexts, it will mean completely different things. So you probably don't want to map this same word into the same point. So we are not going to address this problem by doing this embedding. You see, this embedding will not be able to address this problem. However, what we can do, we can take a word, like, for example, the word quick, and we can assume that whatever surrounds, we have ordering of words, right? They are not just random words. They are ordered in sentences. So instead of just throwing away this order, we can take a window around our word. Let's say this is our word W, okay? And we can say that these two words are W plus. They are related to the word quick, okay? And of course, the word quick will appear many, many times in different places, in different sentences in your text corpus. And it will appear with some within typical context, right? So this is called context. And you will learn these contextual relations. So your metric embedding will not necessarily embody your semantic relations, but what you can infer from the context, okay? So this is how we create positive pairs. Quite simple. It is fully automatic. Of course, you can do many tricks. For example, you can do weights. The farther you are from the word W, the lower is the weight of your word in the context. But again, these are second-order tricks. The idea is that you take positive labels automatically from the text by simply using the location of the words. What about negative labels? What about negative?
Maybe try to find words that doesn't have any similar with, like, if I want to find the opposite of quick, I would look for a word that doesn't have any, that's noted W tag, so W tag pluses won't have any common words with W pluses.
Well, you can do it this way. Let's say there are about, I don't know, probably, let's take a lower bound, about 30,000 words in the English language. If you just pick one by random, the overwhelming probability is that it will be negative, right? So the negative pairs are typically created by simply taking W negative from some noise probability. Let's take it simply uniform over our vocabulary, okay? So this is called contrastive negative sampling in many cases. So you're sampling negative pairs by simply drawing them at random. There will be some label noise. Some of the negative pairs will be misclassified, but the percentage of these misclassified labels will be very small. Okay, so you can clearly deal with it. And now, if we adopt this strategy, we have the following loss function. So let me write it explicitly. Instead of expectation, of course, I have some finite sample approximation. I will take W from the text, all the corpus that I have. Here I will have W plus coming from the context of W in the text. So I'm just scanning my text and I'm extracting these context windows. Negative log P theta 1 theta W plus. And again, remember that these theta W plus, these are just columns in my matrix on which I'm doing the optimization, right? So this is the positive part of the triplet loss. The negative part of the triplet loss, typically, I will sample some fixed number k of negative samples. So it's some W sampled from, let's say, uniform distribution, let's say k times. So actually, these are two sums. I'm sampling k times, so another sum runs over k. Let's write it like this. P theta, 0, theta W minus, and this is our loss. Okay. Of course, we minimize it with respect to theta. So from here, we are just using stochastic gradient, standard training techniques. Actually, it appears to be a very simple neural network, right? The only nonlinear part is the cosine similarity, right? That inner product with the normalization plus the logistic regression that we have, that's all. So the logistic regression, because we are taking the log, actually the argument of the exponential will come out. There will be another term accounting for the denominator, right? That will have this log nonlinearity. And we'll have this dot product with normalization. That's all. It's a very simple neural network. It has quite a lot of degrees of freedom. That's why we typically would like to limit the dimension of the embedding space to a few hundreds, just to make the problem manageable. But again, this is a very simple optimization problem. Okay. Now, what you get is a very interesting vector structure. So, of course, you have a metric structure. So, essentially, the way this problem is phrased in the NLP community, you are trying to predict the context words from the word that you are selecting. So, for example, I would like you to predict the words the and brown from the word quick. Okay, so you can think of it in this way. I prefer to think of it as a metric learning problem. I think it's more useful. But again, we arrive at the same expressions. I'm a little bit omitting some details. For example, in this cosine similarity, you would typically have a bias term that also is part of your optimization variables. But again, these are second-order details. Now, what you get is not only a metric structure where the cosine similarity means something about the usage of the words in your text corpus. You also get a vector structure that is meaningful, that allows you to do interesting calculations. So, of course, it is very difficult to visualize hundreds of dimensions on a flat surface, but we can do, for example, PCA or some more sophisticated dimensionality reduction technique. And let me show you approximate vector relations in 2D. Of course, the original space is, let's say, a few hundred dimensional. For example, this is the point representing the word king. This is the point representing the word queen. This is the point representing the word man. This is the point representing the word woman. Now, pay attention that the difference here is a very similar vector. So what you can do the following operation on the vectors. You can take king. Of course, when I write king, I mean the embedding of the word king, and subtract from it the word man. Okay, so it's king minus man. Add to it the word woman. So typically what you are going to get will be a vector that does not belong to any of your embedding vectors in the vocabulary. So you will find the nearest neighbor, right? And the nearest neighbor unsurprisingly, will be queen. Okay? So once you created this structure, you can do all these kind of manipulations. It doesn't always work this perfectly, but you see, the vectors, the structure of this vector space has meaning. For example, another grammatical meaning of this embedding, for example, you have the verb walking, okay, progressive tense, and the verb walked, past tense. And now we have, for example, the verb swimming and the verb swam. And you see, basically, you have exactly the same differences, or approximately the same differences. You can take, for example, you can take swimming, the verb swimming, plus the difference between walked and walking. And you can transform it into a new grammatical form, which is swam. Okay? And you can find other funny examples. Again, it's not perfect. This is an approximation of your relation that you can create within this metric space. For example, if you take human minus animal, you get ethics. And you can argue whether this is true or not, but at least you can get this kind of representation of the textual corpus, or library minus books, whole. Or for example, Iraq minus violence, Jordan. Again, you can argue about this. Or president minus power, prime minister. So basically, there are many, that was not spoken of Israel. So basically, you can get interesting relations in the vector structure of this space. And what is, of course, very important for our applications is that now we have a finite dimensional vector representing a word. And that can be already operated upon using, for example, a recurrent neural network, right? So that was the end goal of this representation. And indeed, this is a very common way of representing words in language processing applications. Of course, it doesn't take into account the fact that what is called polysemy in linguistics, that the same word with exactly the same writing can have different meanings in different contexts. And in order to cope with that problem, you need to embed not only the word itself, but some surrounding around this word. And there are extensions of the word embedding idea that also embed context. Okay, but these are less common practice than the standard word embedding. Now, what is probably particular about the problem that I showed you? So it was a perfect case of supervised learning, right? It was a binary classification problem with a very simple neural network with very simple nonlinearity, two-layer network essentially. It was this dot product with a softmax. But it wasn't really similar to the supervised learning case that we discussed in other circumstances. We somehow pulled the positive and the negative labels from the data themselves. Nobody really annotated the data, right? So somehow we inferred these labels from the data themselves. So let's try making one further step in this direction. Suppose you have a huge sample of your data and no labels at all. Okay? So you don't have any labels. And you can say, you can draw many pictures. There are many mental images or metaphors or mathematical models that can describe data well, but essentially think of some kind of hypersurface living in some very high-dimensional embedding space. So for example, images, you take a 256 by 256 image, you already find yourself in a hugely dimensional space, right? You have many degrees of freedom. Every pixel is a degree of freedom, right? So I'm drawing just 3 axes, but there are many. But not every image, not every combination of pixels makes an image, right? Most of the images have a lot of structure. And this structure is somehow manifested by the fact that only a tiny amount of this huge embedding space is populated by real samples. So somehow these samples collapse into a very small subspace. And by small, I mean that the number of intrinsic dimensions on this manifold is small. So here you have huge embedding dimension, let's call it n, And here we have intrinsic dimension that is significantly smaller than n. Okay? And again, no labels. You don't know, for example, whether this image is a cat or a dog, or whether this image is an automobile or a chair. But you can still make something useful of this data. So can you infer the structure of this data manifold from the data samples themselves? Okay. So essentially, can you create a parameterization, a coordinate system that will just take up this small n number of degrees of freedom instead of the big N number of degrees of freedom that you would otherwise require to specify in point in this embedding space? Okay. So can you parameterize this manifold? And you don't need labels for that, right? You need to discover the structure of this data. And of course, we know many techniques, or at least we know one very famous technique, very commonly used technique, or commonly abused technique that is employed for dimensionality reduction. It's called PCA, Principal Component Analysis, right? Principal Component Analysis does exactly this. It assumes that our data manifold is a linear space, right? And it models our data manifold as a plane with a prescribed number of dimensions. So essentially what I'm going to ask you to watch in the video lecture is the next chapter that talks about unsupervised learning. And by unsupervised, I mean that there are no labels. Okay, so we're going to discover the structure of the data without making use of any labels. We're just going to use the sampling of the instance space. One of the tools that we are going to mention is the following idea that is called autoencoder. Suppose you start, let me draw it like this. This is your data space. This is your instance X. You pass it through a neural network. And again, here the dimension is very big. Let me draw a very thick arrow. Okay, so there are many dimensions, many degrees of freedom that you have in the raw representation of this data. You pass it through a neural network that is called an encoder, and it will produce a lower dimension representation. The space in which we are going to create this representation, let me call it a latent representation space. Latent because we don't know it ahead of time, right? And then I'm going to apply another network that I'm going to call a decoder that is going to take this latent representation and produce an instance back. Let's call it x hat. And of course, it would be better close to x, right? Now, what happened here is that I created a bottleneck here. This is a bottleneck. I reduced the number of dimensions here, right? So here, let's say I have 10 to the power 6 dimensions, and here maybe I have 10 to the power 2 dimensions. So only the essential information that I need to recreate that instance back will be preserved here. Otherwise, the error here will be very big, right? So this idea is called an autoencoder, and we'll see in the lecture autoencoder. We'll see in the lecture how to construct these things, and a few more ideas. Some of them we'll discuss with you next week. Another very useful thing that you can do with unsupervised learning. So once you created this parameterization of the data manifold, imagine that you now have a black box. You hit a button and you create a new instance here. Okay, so you create a new image out of nothing, right? So in this model, you just pick a point at random here, you decode it with a decoder, and you get some point in the instance space that, if you did the work well, and if it generalizes well, and many other ifs, if it works, it will give you a new instance. Okay? So you have what is called the generative model. You can sample from your potentially very complicated data distribution, right? So you model the data distribution, you can now sample from it. You can generate new images. So give me a new image of a face, okay? And with today's technology, you can get amazing results. Speaking of faces, for example, you can synthesize faces that I argue you will never be able to tell whether these are real faces taken by a camera or faces synthesized using this process. Okay. So basically, these are generative models, and we'll see basically one beautiful trick, which is called generative adversarial training, that will allow to bring the performance of these generative models to unprecedented level. At least it exists for a few years. Probably one of the most useful tricks in this community in the past decade or so. Okay, so this is what is going to happen in the next video lecture, and the next week we are going to talk about generative models. In the tutorial, we are going also to see how to do what is called domain transfer or domain alignment, how you learn on one domain of data and then use that knowledge to apply it to a different domain. Okay, we'll see concrete examples. Good, thanks.